We say that a sequence an converges when limit as n approaches infinity of an approaches a finite number. Otherwise, the sequence diverges. Conveniently, the old limit laws can also be applied to series, which you can pause and view if you wish, but I'd rather move on. So, a sequence an is called increasing if an is less than an plus 1 for all n greater than or equal to 0, which is just a fancy way of saying each term is larger than the previous one. Similarly, it is called decreasing if an is greater than an plus 1, and it's called monotonic if the sequence is either increasing or decreasing. If a sequence never gets bigger than a certain number, we say that it's bounded above, and bounded below if it never gets smaller than a certain number. If it's bounded above and below, the sequence is a bounded sequence. The monotonic sequence theorem says that every bounded monotonic sequence is convergent. Hooray! Moving on to series, which are different from sequences because we add. We take the sum as n goes from 0 to infinity of an, and if this is a number, the series converges. Otherwise, it diverges. Now, we have the first of many tests, the divergence test, which says that if the limit as n goes to infinity of an does not exist, or if limit as n goes to infinity is not equal to 0, then the series is divergent. You should always check this test first, since it's pretty quick and easy. And now we have sigma properties for series, and if you thought I was going to write them all down, you thought wrongly. Onwards to test number 2, the integral test. Suppose f of x is a continuous positive decreasing function on the interval 0 to infinity, and let f of n equal an. If the integral from 0 to infinity of f of x is convergent, then the sum from 0 to infinity of an is convergent, and if the integral is divergent, then the sum is divergent too. Another test, the p-test, which says that the series sum as n goes from 0 to infinity of 1 over n to the power p is convergent if p is greater than 1 and divergent if p is less than or equal to 1. In a stunning turn of event, there are still more tests. Suppose that sum of an and sum of bn are series with positive terms. The comparison test, similar to the comparison test for integrals, says that if the sum of bn is convergent and an is less than or equal to bn for all n, then the sum of an is also convergent. If sum of bn is divergent and an is greater than bn for all n, then the sum of an is also divergent. In addition, the limit comparison test says that if limit as n goes to infinity of an over bn equals c, where c is a finite number and c is greater than 0, then either both series converge or both diverge. And then we have alternating series, where the terms alternate plus minus, bringing us to the alternating series test, which says that if the alternating series is decreasing and limit as n goes to infinity of bn equals 0, then the series is convergent. From this, we also have the alternating series estimation theorem, which says with alternating series, the absolute value of the error, defined as the total sum minus the nth partial sum, is less than or equal to the n plus 1th term. Now, only 2 more tests, I promise. The second to last one is the ratio test, which looks at the limit as n goes to infinity of the absolute value of an plus 1 over an. If this is less than 1, then the series sum as n goes from 0 to infinity of an converges. If it's greater than 1, then the series diverges, and if it equals 1, then the ratio test is inconclusive. And finally, the root test, where we look at the limit as n goes to infinity of the nth root of the absolute value of an. With the exact conclusions as the ratio test, if this is less than 1, then the series converges, greater than 1 diverges, and equal to 1 inconclusive. And with that, we've arrived at power series, which are these epic polynomials of infinite degree. For any power series, you can compute a radius and/or interval of convergence. Basically, for x values does the series converge. An important theorem, the radius theorem, tells us that for a given power series, sum as n goes from 0 to infinity of Cn times the quantity x minus a to the power n, there are only 3 possibilities. First, the series converges only when x equals a. Second, the series converges for all x. And third, there is a positive number r such that the series converges if x minus a is less than r and diverges if x minus a is greater than r. Another cool topic is term-by-term integration and differentiation, where if the power series sum of Cn times x minus a to the power n has a radius of convergence r greater than 0, then the function f of x defined by c0 plus c1 times x minus a plus c2 times x minus a squared is differentiable and therefore continuous on the interval a minus r to a plus r. Then we can differentiate each term to get f prime of x equals c1 plus 2c2 times the quantity x minus a plus 3c3 times quantity x minus a squared plus ... or in a more compact form, sum as n goes from 1 to infinity of n times cn times the quantity x minus a to the power of n minus 1. Similarly, we can integrate each term to get integral of f of x dx equals a constant c plus c naught times x minus a plus c1 times quantity x minus a squared over 2 plus c2 times the quantity x minus a cubed over 3, or just c plus the sum as n goes from 0 to infinity of cn times quantity x minus a to the n plus 1 over n plus 1. And finally, Taylor's theorem, which, not gonna lie, is probably one of the coolest things ever. It says that every function that's analytic can be written as a power series. The Taylor series of a function f of x centered at a is f of x equals the sum as n goes from 0 to infinity of the nth derivative at a over n factorial times the quantity x minus a to the power n. Also, a Taylor series centered at 0 has a special name, a Maclaurin series, which is sum as n goes from 0 to infinity of the nth derivative at 0 over n factorial times x to the power n. In addition, there's the Lagrange error bound, alternatively called the remainder bound for Taylor series, which says that the error is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1, where m is the maximum value of the n plus 1th derivative on some interval. And we conclude with some lovely and beautiful Maclaurin series.